So, thus far in human history, staging has been critical to reaching orbital velocity. So, staging, you've probably heard about it before. When you talk about staging, what you're talking about is you have a rocket here, say that's the payload up on top, and then here's your engine on the bottom, right? Now typically you'll have a stage here, that'd be your first stage. You have a second stage here, and then you have the payload on top. Payload. And generally, what happens here, the idea is, so as you burn fuel, your vehicle gets lighter and lighter, and you don't need mass. You don't need the additional mass of that first stage anymore. So, you have your fuel and oxidizer in here, right? That probably be stacked on top of each other. They could be side by side though. You have fuel and oxidizer in the tanks. Once you've used the majority of your fuel getting out of the atmosphere, you can jettison this extra weight. And historically, those have just been literally jettisoned and dumped into the ocean. So you have a rocket take off, and as it flies, at some point, when it's reached space, it separates from its first stage and continues the second stage only. And then that first stage is either goes and splashes into the water, or obviously in the case of SpaceX in the last 5 years, right, you could potentially land that stage on a ship or even on land if your energy is low enough. Meanwhile, your second stage will continue its trajectory, burning fuel and oxidizer to actually reach orbit. So, why is this necessary? Well, there's a more complex equation that we'll get into in more detail later, but basically, there's a theoretical minimum amount of fuel you need to get into orbit, and that is based on the efficiency of the current kind of chemical propellants we have, of which our propellants, as described in our last lecture, were most common is RB1 and liquid hydrogen for our fuel. There's also different kinds of monopropellant, and methane is a new one that SpaceX and Blue Origin are working on. But for any of these kinds of chemical combustion, you're limited in efficiency. Even liquid hydrogen, which has the highest efficiency of all of those, at sea level doesn't have enough efficiency to make a single stage orbit work. Anyway, so the theoretical minimum amount of fuel you need to get to orbit is about 10 times your payload mass. So max theoretical payload mass, we'll say is, I'll do it in red just so it's a little more, we'll say is about equal to 10% of your total mass. Now that's definitely max theoretical, right? That is not that's not realistic. So the Saturn V, I believe, had mass fractions of, I think, 3 to 5%. So somewhere around 5% is a much more realistic number. So we'll say 5% is realistic for your payload fraction. So, and with this 5% payload mass, we can do some calculations to figure out how much of a difference staging is really making. So let's talk about a rocket real quick. So what are the things that are making up the weight of the rocket? Well, we've drawn a two-stage rocket here. Well, you've got your fuel. This is your largest weight. Fuel and oxidizer, right? Both of which, I just generally say are fuel because that's what's required to create combustion to cause you to go. Next is your structure. so the launch vehicle itself, and then third is your payload. Now, so your payload, as we said, you can expect realistically about 5% of your mass to be payload. Structure is, so for structure, that's, the weight of the rocket itself. The lowest ever dry mass for a rocket was actually the early Atlas rockets, and the dry mass of the vehicle as a percent of the total vehicle mass, so including fuel and payload, was only about 5%. Only about 5% of the mass was actually the structure, the metal making up the rocket itself. But that's because the rocket actually used internal pressurization, and the rocket would actually collapse under its own weight if it were not pressurized. So, if you can imagine a balloon, essentially, the air is required for it to maintain structural integrity. And this was, early Atlas rockets. They were actually pressurized at about 5 psi. And if they lost pressurization, they would collapse under their own weight. So obviously that's one extreme end of the mass percentage of your structure as a total percentage of vehicle mass. So, that's 5%. We'll say more realistic is about 10%. That's where most vehicles are going to lie. About 10% of your mass is made up of structure. So that leaves 85% of the mass of the vehicle is made up of fuel. Now, of course, as you burn fuel, your structure and your payload become larger and larger percentages of your overall mass. And we can do some calculations to prove this. So we'll start with a Falcon 9 or an Atlas V size rocket, just because those are the most common rockets flying today. It's ones that people are very familiar with, and they're kind of the heavy hitters for modern rockets. So Atlas V or Falcon 9. Total weight, so M total is about equal to 1,000,000 pounds. It's actually more like 1,200,000 for a Falcon 9 full thrust, or 1,300,000 for an Atlas V. Now, obviously, that's going to vary depending on your Atlas V variant. There's a number of different variants. They can have different numbers of side boosters and that kind of thing, but we'll say that our total mass is about 1,000,000 pounds. That's a nice round number that's going to make our calculations simple. So, if we say that our vehicle mass is 1,000,000 pounds, we know that fuel and oxygen makes up 85% of that. So now, we're going to burn fuel as we fly, obviously. So the majority of your fuel really is required just to leave Earth's surface. So most of your mass is actually just getting out of the atmosphere, getting vertical, and getting started on that horizontal path and turned over. So really, by the time you reach, I think you're probably about 1/3 of your velocity, and I'm not sure about altitude, honestly. It's going to depend on your orbit, but we'll say about half of your altitude. You'll have burned about 70% of your fuel. Now, these are rough numbers that I'm making up, but you get the idea. So at this point, you've only achieved 1/3 of your velocity, and you're only at half of the necessary altitude, but you've burned about 70% of your fuel. So why is that? Well, as we've discussed, it's because the atmosphere is a lot thicker down here. It requires a lot more force to get through the lower parts of the atmosphere, and as you exit the atmosphere, it just becomes easier and easier. Also, your vehicle is getting lighter and lighter, but as you burn down fuel, so your acceleration is getting higher. So the rate at which your velocity increases is also increasing. So it makes sense when you think about it from that perspective that we only have 1/3 of our velocity and we've spent 70% of our fuel, but we're going to get a lot more out of the remaining 30% of our fuel. And that's sort of where staging comes into play. So say, since we burned 70% of our fuel, say we are able to jettison 70% of the weight of our rocket. I mean, why have, say you had a single stage rocket, right? Why would you have this giant rocket that has 30% capacity of fuel and 30% capacity of oxygen? It just doesn't make sense. The rocket's mainly empty. It would make more sense if instead you said, okay, now this is assuming, this is basically totally factoring out reusability, right? We're assuming that rocket stages can't be reused, which was the main assumption for the majority of history of spaceflight, really. And I understand that's obviously not a valid assumption anymore. But even with reusable rockets, as SpaceX has shown, staging still makes a lot of sense. So anyway, here you've got your first stage and your second stage. Fuel or oxygen could be at the top. I'm just showing. So if you can get rid of all this mass, so I actually drew this incorrectly. This is full, and this one is empty. Now, if you can get rid of all this mass, so that's 0.7. Well, yeah, that's 0.7 of your M structure, right? It actually makes a lot of sense because, F equals MA, your mass goes down. If the force stays the same, assuming that your second stage engine is as as high thrust as your first stage engine, then obviously your acceleration is going to go up. And even if it doesn't, your acceleration for the amount of fuel you burn will go up. So it's much more efficient to not have all that dead mass here lugging around. So let's see what happens when we work the math on this. So we know that our rocket, our M total is 1 million pounds. I'm just going to say 1 times 10 to the 6th pounds. Of that, our M fuel we said was 85%, right? So that's 8.5 times 10 to the 5th. Our mass of payload, is, what did I say, 5%? 0.5 times 10 to the 4th, right? And then our mass of rocket, or structure, I'll say structure, is equal to the remaining 10%. So 1 times 10 to the 5th. So now we know that at this point we've burned about 70% of our fuel. So let's say that at this stage, or this point in our flight, we chose to get rid of, conduct a staging operation and get rid of some of our mass. So our mass fuel went from 8.5 times 10 to the 5th times 0.3. Our fuel mass is now 2.55 times 10 to the 5th. Our payload mass is still going to be 0.5 times 10 to the 4th, right? And our structure mass is still going to be 1 times 10 to the 5th. So when you add all those up, 100,000 pounds of structure and 50,000 pounds of payload, you get M total equal to 405,000 pounds, 4.05 times 10 to the 5th, of which now your structure is actually equal to about 25% of your total mass. Now, say you're able to jettison, 70% of that mass. So now you would be dropping your M structure from 1 times 10 to the 5th to 3 times 10 to the 4th. substantial reduction. We change that to 3 times 10 to the 4th. We'll add that back in, 30,000 plus 50,000 plus 255,000. U in total is going to be 335,000. And with an M total of 335,000, that means we dropped our total mass by, what is that, 405,000 minus 335,000, what is that, 70,000, right? So 70K, which is, divided by 405,000 is about 17%. So we had a roughly 17% weight reduction by staging. So keep in mind, I made these numbers up. They are rough order of magnitude, but they should be somewhat accurate. I'm willing to bet it's within, 10 to 30% of your weight reduction by staging. Obviously that's going to vary based on the vehicle that you're using, but this is going to be a good estimate for how much weight you're actually reducing by staging. So, you may wonder, well, if it's only 17% weight reduction, why is that big of a deal? Well, this weight that you're reducing by staging is going to directly affect both how much payload you're able to take into orbit, and remember, the only reason for a launch vehicle's existence is to take payload into orbit. And even though you've used 70% of your fuel, you still only have 1/3 of the velocity you need. So really, you have 2/3 of your mission left to go, and that weight reduction is going to make a huge difference in how much fuel it actually takes to get into orbit. And this just kind of demonstrates also how much of rocketry and I guess launch vehicle operations are done on the margin, where it's only 17%, but 17% makes a huge difference, even if it's 17% for 2/3 of the flight. That's absolutely critical to get into orbit. So staging is absolutely essential with the technology we have right now. I'll say that. And you see that with even companies like SpaceX, who are very willing to take risk. Staging just makes a lot of sense. Now, staging especially makes sense, obviously, if you're able to land your first stage and recover it, as SpaceX has demonstrated many, many times, and I think in excess of 70 times now. They're able to land their first stage and reuse it for a later flight. And this obviously reduced their operating costs. It also reduced their time between flights. So it results in some really great economies of scale for them. And they've been getting faster and faster with their turnaround times, and lots of good stuff going on there. Alright, and I just want to point out that we'll go into much more detail about staging and some of the real math that you do, instead of these just order of magnitude calculations. We'll talk about some of the real math that you do to calculate staging. So how is staging carried out? So as I've shown here, several times now, I show the rocket go up and it loses the stage, and the stage either splashes in the water or comes and lands on a ship. Well, that's only one kind of staging. That's called series staging, where you have one stage on top of another. There's another kind of staging called parallel staging, where you have multiple vehicles on the bottom, and these could be, they could be identical liquid rocket booster or liquid rocket engines, like the Falcon Heavy, or they could be solid rocket motors in the case of the Space Shuttle, or the Alice 5 uses solid rocket motors as well. And there's some different reasons for that. Generally, your side boosters are going to be jettisoned first, and a lot of times, so because they'll be jettisoned first, they're going to be in the thickest part of the atmosphere. So there's some math that goes into it, but basically a rocket engine, you want to be more depth than we need to go into right now, but basically a rocket engine, you want it to be the right size for the atmosphere. So when the atmosphere is thicker, you want the nozzle to be smaller. when the atmosphere is less thick, less dense, I should say, you want the nozzle to be larger, so that the gas exits at a lower pressure, basically. And because you want the gas to exit at the same pressure as ambient pressure. Anyway, that's one reason for staging also, really, is that it allows you to use engines that are optimized for sea level or close to sea level on your lower portions of the stages, and then your upper stage can maybe have a vacuum optimized nozzle, which is going to greatly increase your efficiency. Anyway, as I was saying though, a reason for using a solid rocket booster as opposed to a liquid booster when you're low in the atmosphere is solid rocket motors tend to have higher thrust to weight ratio. So SRB generally, I'm not going to make any promises, but generally higher thrust to weight, which means they provide that oomph you need to get out of the atmosphere quickly, and then your liquid rocket engines provide the efficiency that you need to do a sustained burn to get into orbit without wasting any crazy amount of fuel. That being said, you could really do liquid or solid. There's a variety of considerations that we'll go into in a different video. So series staging, parallel staging is used occasionally, often in rockets like the Falcon Heavy or the Delta IV Heavy, where hey, we need to carry more payload. What can we do relatively easily? All right, let's strap 2 boosters on the side and make this thing work. Whereas series staging is generally, it can operate somewhat like that, but it's generally designed into the vehicle earlier on, and almost all rockets use some form of series staging. The Space Shuttle might be one of few exceptions, but generally rockets will do series staging, and that just allows them to get rid of the majority of the mass in that main vehicle, and it allows them to use a under-expanded nozzle, or sorry, a nozzle that's properly expanded for operation in a vacuum. Okay, so we'll get into staging a lot more in future videos, but for now, that's going to cover it. I think I covered everything I needed to, so we'll go on to another topic about launch vehicles that I want to cover before we end, and that's air versus ground launch.